Hello? Okay. Let's start straight away. Ooh, the volume is really high. All right. Okay, today we talk about vibrations. And then, after the break, we'll have a look at the second exercise of the PST. I'll just go through it again to talk about a bit of stuff. I've received a couple of questions, so I can clarify to everyone in the meantime. Nothing major. Okay, vibrations. Okay, so vibrations are a very particular type of motion. Okay? So still dynamics, there's still forces involved, there's still motion involved. But it's a very particular application. And that's why it's very studied, very much studied in dynamics. So there's a whole branch of dynamics which basically studies vibration. Okay? Why is that? Any idea? Why vibration and not some other type of motion? Anyone has any idea why vibration are important? Or yes. So basically, every machine, structure, whatever, system, dynamic system, it's going to vibrate. Okay? So usually, in most cases, the vast majority of cases, vibration is an unwanted thing, not a wanted thing. Okay? So imagine when you drive your car, and you feel some vibration on the driving wheel. What's that usually? Come on, a lot of people usually know what's that. Usually. It can be a lot of things, but very commonly is that your front wheels are not perfectly aligned, right? So if they're not, when they set up your steering, when you change tires and stuff, they need to be sure that your front wheels are aligned. If they're not, you get some vibrations on your steering wheel, basically, because your car gets a bit of wobbly motion. Okay? So, and this is an example in which vibration is actually used as a symptom of something else that goes wrong, okay? In that case, it's not that vibration is so bad. Okay, you get a bit of massage while you're driving. It's not too bad, but you know that there's something wrong. So vibration is also used a lot for condition monitoring. So vibration is a symptom that there is something wrong in the system very often. But vibration itself, it's a problem sometimes, okay? So imagine if you are, if you have a building, okay, and there's an earthquake, the building will vibrate following the earthquake. If it vibrates too much, what happens? Internal stress is high, because big vibration means big deformation of the building. Do you agree? Big deformation means big stress. You know that sigma equal E epsilon, right? So big epsilon, big sigma. Big stress means failure. Usually fatigue failure, because vibration is not just a constant stress. It's a stress that goes positive, negative, positive, negative, positive, negative. That's even worse, because you know that fatigue. Have you seen fatigue in any other unit yet? No? Fatigue? No? Okay, you'll see it. It's not fundamental for today, just to see it. So if you subject the body to a cyclic stress, so if this pen, I put a certain load on this pen and I keep it constant, it's much better than if I do that. You know intuitively. Even if the amount of load is the same, if I put it cyclically, it's much worse on the body. Okay, that's fatigue, called fatigue. That's phenomenon that makes it worse. Okay, vibration so creates stress into structures, not only stress, cyclic stress. So yes, I mean compression, elongation, compression, elongation, compression, elongation, compression, elongation, and that's very bad for structures. And you will see it in a stress unit very soon, I'm sure. Okay? Good, so we want to study vibration to see how much our system, our particle, vibrates given a certain situation, okay? And today we look at free vibration. So there are two main distinctions of vibration, free and forced. Forced means there is an actual external force which keeps the body into vibration, into vibrating, okay? So, for instance, take this beam. If I continuously hit it, my hand continuously applies a force to this beam. This continuously vibrates. Makes sense, right? Another type of force, of vibration is free vibration. That means that I take the beam, I take my system to a certain position, I let it go. There's no force applied to the system that makes it vibrate. It still vibrates because of its initial position, okay? That's free vibration. Clear? So today we look at free vibration, and then next time we look at forced vibration. Okay? Cool. Okay, so vibration, if this thing stops, okay. Vibration is studied very often taking systems and modeling the system into three different types of components. Bodies, or particles, okay? In this system here, what's the body? This beam. That's the mass of the system, okay? That constitute the mass. Springs, that looks like it. And dampers. Okay? What's a damper? Well, you know, the thing you have in front of your bike if you have a fancy bike. Okay? And we'll see what do dampers do exactly. In this system, the damper is actually represented by the spring itself, some air resistance and other stuff. And we'll see later what it means. Okay, so what's the important law for each of those systems? Well, the mass immediately reminds us of Newton's law, right? You think of a mass, you think, oh, F equal ma, right? The springs, there's a law called Hooke's law, which is that one, which tells me that if I extend a spring by a certain amount delta L, so if I pull it by, say, 1 centimeter, the spring will give me a force back, which is a certain constant multiplied that elongation. So the more I pull, the bigger the force I get back from the spring. Okay? Is it clear? Does it make sense? Damper has a similar relationship, but the force that the dampers gives me is proportional to the velocity at which I'm elongating the damper, not the amount. So if I do it very slowly, almost no force. If I pull very fast, I get a big force, big resistance from the damper. I get a big force pulling me back. Okay? Is it clear? Think about it. If you take a damper, this damper's in front of the bike, if you do that, there's a spring inside too, so it's not really only a damper, it's a damper spring, that damper of the bike. But if you take an actual damper, and if you squeeze it very slowly, it's very easy to do it. If you squeeze it very fast, it's hard, because the force that you receive back is proportional to the velocity or the speed with which you actually compress it or extend it. Clear? And the direction of these forces is obviously opposite to the direction of motion, right? So a spring, if I pull this way, I get a force that way, obviously, right? Imagine, I should have another spring in here. This is a crappy spring, this is a better spring. For people at home. That's a lot of light. Okay. So this is the spring. If I pull it this way, the spring is pulling my hand back towards the center of the spring. If I compress the spring, so if I move that way, the force is given to me that way. Okay? So the force that the spring gives back is the opposite to the direction in which you are squeezing it or pulling it. Okay? Clear? Same thing for the damper, obviously. If you pull the damper, it will pull you back. If you push the damper, you squeeze the damper, it will resist your squeezing. Okay? Putting a force the other way. All right. Okay. Vibration is a particular type of motion which is defined by two things. One is that it's small. You don't expect vibration to be of the size of your body. Okay? So imagine you have a car, okay? Right? You turn on the engine, you see your car is vibrating, kind of thing, right? Possibly. Now, this vibration won't be 2 meters, which is the size of the car. It will be very tiny compared to the size of your system. If you have a building vibrates, tall building. Okay? How much will a building vibrate? What do you think? Let's say one William Street, the tall building thing. How much do you think it will vibrate on the top? A building like that. Order of magnitude. Okay. Millimeters, centimeter, meter, kilometers. I'm talking the vibration amplitude. Meter. Okay? So the vibration amplitude is actually meter for this kind of buildings. A meter. 2 meters, something like that. Now, I don't know William I. I don't even know how tall it is. But this type of building, the order of magnitude is a few meters, the vibration, okay? There are some nice video. Maybe I dig them out during the break of actual building vibrations. And that's normal. That's okay. Why? Because the building is so big that a meter on top doesn't change much the shape of the building, so the actual deformation is not so big, so the stress is not great, okay? It's vibration. 1 meter over 200 meters, not too much. So it's still small compared to the size of the system. And it's around an equilibrium point. So actually, we won't use this property of vibration in this unit. We don't need it because we only look at the linear system for this unit for vibration. But so we won't use much this property of the fact that displacement is small. But we'll definitely use the second one. It's around an equilibrium point. Okay? What's an equilibrium point? The point at which, if I don't touch the system, it will stay there. So look at this bar. This is obviously its equilibrium position, the one at which it stays if I don't touch it. All right? All the forces are perfectly in balance here. Gravity is balanced by the spring, and therefore the bar is still. Doesn't accelerate, doesn't move. Okay? When it vibrates, when it has free vibration, it vibrates around that position. A little bit above, a little bit below. Is it clear? And the center of this motion is that equilibrium position. It moves from here to here, from here to here, but around that equilibrium position. Clear? And the easiest way to find it is actually this. To find the equilibrium position, I need to find the position in which all the static forces, all the forces that are constant, like gravity and everything there, are in balance. Okay? In this case, I have force, gravity, and the spring. I have these two forces acting on this body. So gravity and the spring must apply equivalent moments to this system, not to stay there. To stay there. Okay? We'll see a simple case here. Okay. As I said, 2 cases, free vibration, that system on top, this system. There is no external force. I only apply an external force at the beginning to bring the system to a non-equilibrium position, and then I drop it from there. That's free vibration. Is it clear? So look at this system. Now it's in equilibrium. It's fine by himself. Okay? Very happy as it is. Now, I poke him. So I put a force there that brings him in an equilibrium, in a position which is not the equilibrium position, and then I drop it. That will vibrate around the equilibrium position, which was the position at which it was at the beginning if nobody touches it. That's free vibration. So I move my system from the equilibrium position, and then I let it go without any other force. Okay, is it clear? Top case. Force vibration, I instead put a force in here which continuously pokes the system and makes it vibrate. Okay? Good. So in the case of free vibration, vibration is only due to the fact that the system at the beginning, it was not in the equilibrium position. Is it clear? So if I don't move it from here, the system will not vibrate. Once I start moving it, at the beginning it was not in the equilibrium position, then it vibrates. That's the only reason why it vibrates in case of free vibration. In forced vibration, of course, it vibrates because there is a force there which shakes it. But today we focus on this. Good. Another classification. Vibration is classified as undamped if there is no damper, and damped if there are damping elements, one or more. Okay? What do you think is the difference between the two, intuitively? If there is no damper, what happens? Yes, and that's what it causes in practice. What happens then? But it oscillates in every case. I mean, it oscillates also if there is a damper, possibly. It never stops. It oscillates forever. In theory, if there is no damper, the system will oscillate forever. Okay? In practice, does this case ever exist? No, it would be perpetual motion. Okay? There is always a little bit of damping. Is it a good thing or a bad thing? Okay, in 99% of the cases, is it a good thing or a bad thing? Any idea? What did we say? Usually vibrations are wanted or unwanted? Unwanted, so usually it's a good thing, because at least they stop. We have them, but they're kind of kept together by that damping there. Okay, so usually damping actually helps us. And since we are engineers and we like to create ourselves trouble, for that reason, we very often neglect damping. Because we say, well, damping is only going to help us. So if I solve my problem without damping, and it's still okay, well, it's going to be just better. Okay? That's not actually always true. Sometimes damping does some weird stuff if your vibration is forced, not free, and we'll see it next time. But very often, not very often is too much. Say 70% of the times, especially with complex structures where vibration is not simply one mass and one spring, damping is so complicated that it's very difficult to model, and we simply neglect it. But if we can, we model it, because then it's more precise. Okay? Questions? Very general so far. Don't worry, math is going to come. Okay. How do I solve a vibration problem? You already saw it, but I hope you forgot it. How do I solve a vibration problem? How would you approach a vibration problem? Is it a dynamics problem, or is it something a bit different? No, it's a dynamic problem. I mean, we've seen so far masses, springs, and no dampers, no, but yeah, not too bad. So we solve it as any other dynamic problem. Okay? We draw the free body diagram, write Newton's law, blah, blah, blah. So we draw a free body diagram, decide coordinate system, and write the equation of motion through Newton's law and a bit of kinematics if you need it. Okay? So in this case, it's pretty simple. Free body diagram is this one. Everybody agrees? Which forces act on this mass? Well, the spring, gravity. What was that? Ooh, the ghost. Okay. R, okay? That's N usually we call it. I'm going to call it N. R. We usually call it N, so I call it N. Okay? By the way, I changed a bit of notations in this slide later. So if you have downloaded the slides before this morning, probably you're better off downloading them again after the lecture, because I'm going to fix them again during the lecture, as usual. It's not that they were wrong before, but I decided to change a bit of notation just to be even clearer. Okay, anyway, so this mass is subject to spring force, gravity, and the reaction force from the ground. Okay? In vertical direction, I know it's not very interesting because there's this ground, so it's not going to move. I don't even write Newton's law in vertical direction because I know y dot dot is equal to 0, so I won't get much interesting motion there. I write only horizontal, so I can write that mx dot dot is equal k delta L. How much is delta L? Well, delta L is equal to x. The elongation of the spring is equal to how much I move that mass, obviously, if the mass is attached to the spring. Do you agree? So I end up minus kx, because this force is going the other way, equal mx dot dot. Everybody agrees here? Or do I need to do it on a piece of paper? I'll do other exercises later on a piece of paper. If you agree 95% with this, we are all right. Okay? So Newton's law looked like this. Is this an equation of motion? It is. I'll rewrite it in this shape. Okay? So, something weird happened here. Okay, so I look at this equation. I write it this way, and this is obviously an equation of motion. This m, I assume I know the mass of this system. I assume I know the stiffness of this spring. And therefore, this equation is the only unknown is the actual motion x and its second derivative. So it's a differential equation. Okay? You remember we've obtained similar differential equations when we did. You remember that exercise of the skier going up this curved path? We've obtained a very complicated differential equation with theta dots, theta dot squared, theta dot dot, very complicated one. And we said what at that point? Oh, you need a computer to solve it. Okay? That equation we found, and there are other equations, complicated equations that you can find in a complicated equation of motion. If they are too complicated, you have to solve it in the computer. Do you think this equation you can solve it or not? Analytically, I mean, without a computer. Yes, you can. This is a linear ODE, ordinary differential equation, linear coefficient ODE. Okay? So it has a very simple solution. Actually, all vibrating systems which are undamped, they end up in an equation which looks like this. And I wrote it this way. Okay? All systems which vibrate with 1 degree of freedom, so there's only one body moving, let's say. Doesn't matter how many springs, how many dampers, and how the system is tilted, is vertical, it's just whatever. You always get this kind of equation where m star is a certain number and k star is a certain number. In this particular case, m is equal to the mass of the body and k is the stiffness of the spring. It's very simple. Okay? But in general, they always take this shape. Sometimes m is something more and k is something more, but you always end up with an equation like that. When you have a single degree of freedom, undamped vibration, free vibration. Okay? So there's no force, there's no damper, and you have only 1 degree of freedom, so only one thing that can move. Okay? Clear? Why is that interesting? Well, because if it's always like this, Once we know the solution to this equation, we don't even need to actually solve this equation. We already know that solution is always the same because the equation is always the same. Okay? And the solution is this one. So you will know that x of t, I'm going to write of t just to remind you that it's a function of time. It's the motion of the system, how x moves in time. It moves this way. So it's a sine of time with a certain amplitude, a certain frequency, and a certain phase. These are the three characteristics of vibration. Okay? Once you know these three numbers, you know how your system is going to move. What's amplitude physically? If this thing is vibrating, what does A tell me? Exactly. How much it vibrates one side and the other maximum. Like what are the limit points of the vibration? That's A. Is it important for engineers? Is it one of, I'll tell you that out of these three parameters, two are the most important. The other one is way less important. Is A one of the important ones or not? Why is it important? Well, exactly. I mean, I want to know how much it vibrates. That tells me how much. Is it 1 meter or 7 meters? It's pretty different, right? If I'm on top of the building and it's 7 meters, I will see the motion myself and I'll be scared. If it's 1 meter, maybe if I'm far from everything, I won't notice that it's moving, so it's good. Okay? Just a stupid example, but just to say that obviously the amount of vibration is interesting. Okay? Another very typical case of vibration, actually is the most probably studied vibration problem, is rotors, okay? Turbines. Turbines vibrate, okay? They are long shafts which are quite flexible, and their bearings are also allow some little movement. Therefore, this turbine, while it rotates, vibrates. Now, what happens if it vibrates too much? Any idea? That's one of the problems. Of course, fatigue on the shaft will develop some crack in the shaft, so the stress is going to be bad for the stress. But even earlier, if it vibrates too much, what happens? It touches. It rubs. Imagine your pallets are rotating within a certain gap that's left there, right? If this thing shakes like crazy, these pallets are going to hit the stator part, okay? So vibrations in turbines are studied a lot for this reason, because there are very tiny tolerances for fluid dynamic purposes, and you don't want the vibration to be big enough that it creates a rubbing between moving part and static parts, okay? So that's why amplitude is interesting in that case, obviously. You want to know if the amplitude of vibration is bigger than the gap you have, because if it's bigger, that's big trouble, it's going to hit. Good. Let's move to the next parameter, frequency. What is that frequency telling me? Oh, sorry. What's the unit of A? Because to understand, I'm not saying suggestion forever as engineers. If you want to understand a quantity, first thing, think about what unit it has. Because if you understand the unit, you kind of figure out what it is. So what's the unit of A? Meters, or millimeters, or microns, but it's an amount of vibration, right? Good. The unit of omega n is radians per second. It's a weird unit. What is it? Looks like an angular speed, but it's not really in this case, despite the unit being the same. If you divide it by 2 pi, is 1/2, is hertz, which means times per second. Okay? If you divide it by 2 pi, that quantity, it becomes a natural frequency in hertz. So that tells me how many times this thing vibrates in a second. Okay? Is it clear? That quantity is connected to that. There's a 2 pi factor in between. So if the frequency is high, it means that thing will vibrate very fast. It won't change the amplitude. If the amplitude is the amplitude, that's it. Okay? Once you have A is the amplitude. You know it's vibrating plus minus 1 meter. But in that space, it can vibrate very fast or very slow. Okay? And that's the parameter. What about phase? What is phase? It tells me where it starts. Does it start like this, like this, like this? So where in the cycle this vibration is, okay? Obviously, if this phase psi is equal to 0, how much is the amplitude at time equal to 0? So at the beginning of the vibration, if this phi is equal to 0. Sine of 0 plus 0 becomes 0. Sine of 0 is 0, so it's nothing. So if the phase is equal to 0, it means it starts from here at the beginning. Okay? If the phase is equal 90 degrees, well, then at time equal to 0, I have sine of 0 plus 90 degrees. Sine of 90 degrees is 1. So the amplitude, so the x is equal a at time equal to 0. It means it starts from here. If this is the amplitude, it starts from here. Okay? And then it vibrates like this. Instead, if that psi was equal to 0, it started like this and then vibrated like this. If psi is minus 90, it starts from here. And then it vibrates like this, and so on. What do you think is the most important one between omega n and psi? This is a more difficult question than the previous one. And you will actually fully understand it only next time. But which one will characterize the motion more? Omega or psi? Or frequency or phase? Who says frequency? Who says phase? Frequency is more important. Why? I'll tell you why phase is not so greatly important. Do you really care where it starts? I mean, it's going to vibrate then, right? It depends on your definition of time, too. Where is time equal to 0? You have to decide what time equal to 0 is. So it's a bit... I mean, is it really relevant? Think about an engineering case in which you are checking if your vibration is within a certain limit and it's doing some stuff. Where it starts, not really relevant because it's going to go through all the positions anyway at a certain point, right? So phase is usually considered less important than frequency because frequency tells me something about how the motion happens, how fast the motion happens, okay? Is it clear? Kind of. It doesn't need to be super clear till now. Omega n, we'll see it next time. It's very important in forced vibration because that's the natural frequency. I can already spoil a bit next lecture. When you force a system, when you force it with a frequency, with a force that has a frequency which is the same as the natural frequency, that system will vibrate a lot. Big amplitude. Okay? We'll talk about it next time, otherwise it's going to be too much. Okay, the formulas for amplitude and phase are here. Obviously, intuitively, amplitude depends on x0, which is the position at time 0, and the velocity at time 0, the speed at time 0. Okay? What does it mean? If I have if at time equal to 0, I have just a tiny displacement from here and 0 velocity, that's not going to vibrate much. Agreed? If I have a massive displacement at the beginning and I drop it, that's going to vibrate much more. If in the same way I give a very initial velocity at the beginning, it's very difficult to do with this thing, but I hit it fast at the beginning, that's going to vibrate a lot. If I just give it a tiny initial velocity at the beginning, it will vibrate less. Okay? So the initial disturbance from equilibrium, both in position or in initial velocity, the biggest the vibration will be, is intuitively kind of understandable. Do you agree with that? The phase is related to the ratio between the two. But we said it's less important, so I'm not going to spend too much time on that. Okay? Cool. This is the most important thing. What does natural frequency depend on? Look at it. Stiffness and mass. How is this thing different from A and psi? What is not there in this formula? There's nothing about the initial condition. Okay? That's why we say that the natural frequency is a property of the system itself. It doesn't depend what you do to the system. It doesn't depend, it doesn't matter if I push it a lot or if I push it just a tiny bit. The frequency of the vibration is going to be the same. Galileo discovered that with the pendulum experiment. It doesn't matter if you pull the pendulum a lot or you pull it a bit. It's actually not completely true because the pendulum is nonlinear. But if you pull it a little bit or a little bit multiplied by 2, it won't change omega. Okay? And in this system, when you have a spring and a mass, if you pull the mass at the beginning by 10 centimeters and you drop it, or if you pull it by 20 centimeters and you release it from there, the frequency is going to be the same. The time it takes to go from here back to here, it's going to be the same. The amplitude will change, obviously, because if you pull it more, it will vibrate more. But the time it takes to make one cycle will be the same. Clear? That depends only on the property of the system. So you don't need to know anything about what do you do to the system. As long as you have all the property of the system, you can calculate the natural frequency. Questions? If the force is no, in general, no. If the force doesn't depend on the motion itself, no. So if the force is a force which you impose, no. Okay? The natural frequency doesn't. The vibration frequency will be different. The frequency of the vibration will be different. The natural frequency doesn't. Of course, the vibration, it's next time lecture, but if I force this system with, say, 1 hit per second, how much will it vibrate at 1 hit per second? So the system will always vibrate the same frequency of the force you're putting if you're talking about forced vibration. Okay? But in this case, there's no force, so the free system is free to vibrate at whatever frequency it wants. And if that's the case, the system will vibrate at its natural frequency. And the natural frequency depends only on the property of the system. Okay? Have I partly at least answered it? Okay. So in this case, the vibration, the equation of motion is this one, and the solution of this equation is this equation. So the vibration will look like this in time with this parameter equal to that. Well, in this case, it's just K. So if the stiffness is 100 and the mass is 1, the natural and the mass is 1, then omega n will be square root of 100 over 1, which is 10, and so on, okay? And this is the amplitude, and this is the angle. Okay? Clear? That's how it looks. Another suggestion in general, when you see a function, the best thing to do is draw it and understand what it is. Okay? This shows you in time how the displacement, so x changes. Okay? And I've put these quantities. I've done an example with k equal 1,000, m equal 1, x0 equal 10 centimeter, and v0 3 meters per second. So what happens is I have a sine wave. The solution is a sine wave whose a is about 0.12 meters. That's the amplitude. And I get it putting in this number in here, this number in here, and omega n in here. The frequency, which is related to how much does it take to go from here back to here, okay, that's related to the frequency of the vibration. That frequency is obtained by square root of k over m. Why is it stars? Oh, no, it's the next slide. And the phase, which is what's the starting point, basically. It's related to the starting point. Well, it's calculated this way. Okay? Clear? So the idea is, if you know M and K, and you know X0 and V0, so if you know the properties of your system and the initial condition, you will know how free vibration looks like in time. It looks like this, with this number equal to square root of these numbers, this number equal to square root of these numbers, and this number equal arctangent of these numbers. Clear? You know all the numbers, you can find fully the solution. Okay? You don't actually need to solve this equation because you know that once you find this equation, the solution is always this one. You just have to find the numbers based on which number you have here and which number you have here. Clear? When I said that this is related to how much it takes to come from here back to here, well, that's the relationship. The period, I'm sorry for T. T is a lot of stuff in this unit, but they call it like this. Okay? Period is often called T as well, like kinetic energy is called T, and tension is called T. Unfortunately, they use it like that. I didn't choose it myself. Okay? I would have called period P, but unfortunately, they decided T. Okay. So the period, which is in which unit? What is the unit of the period? Seconds. It's how many seconds it takes to come back to a certain position. Okay? So, or to complete one cycle, if you want, of the vibration. Okay? That is 2 pi divided by this number. So once you know the natural the frequency of the vibration, the period is 2 pi over that frequency. Clear? So when you're asked to draw stuff like this, you can draw it even by hand if you want. Okay? Clear? Because, well, the amplitude will tell you how big the sine is, and with the frequency you can calculate how large is this gap here between 2 peaks. Okay? The phase, I usually am very tolerant. If I ask to plot it by hand, then I tell you, the phase, just forget it. If you plot it with computer, you simply put the number in this thing, and the phase will be calculated automatically. Okay? Good. Let's add one little bit of complexity. What happens if that system, instead of being horizontal, it's vertical? Okay? So I actually have one of those systems here. So this system. Let's see if I'm able to do this. Fantastic. No, it's upside down. Nope. There is no upside down thing. Maybe fine. No way of rotating it. Okay, this way it doesn't look too odd. Okay? Only does a bit, but whatever. Maybe like this. Well, it's upside down. I'm sorry. Okay, now. Cool. So this is the mass. What happens? Let's say I have the mass. Or better, let's say I have the spring without the mass. Spring without the mass. Okay? And then I put a mass there, and I leave it. What happens first? Well, the spring will going to get elongated by gravity, correct? Okay, spring so elongates, and then if I do something to the mass, like I hit it, it starts vibrating, okay? It does. Clear? Cool, that's enough for this. Okay, so let's go on. So what happens is this. So conceptually, if I have a spring, I attach the spring here. This is, oops. That's better. That's even better. So let's start with this situation. Spring by itself has a certain length. Okay? If I attach something, that thing will drop, will elongate that spring because of gravity. Okay? And it goes into here. This is the equilibrium position. When I said vibration happened around the equilibrium position, I meant that now its system starts vibrating around this point, up and down from here, not from here. Okay? Clear? In horizontal position, it doesn't have any difference because there's no initial elongation because it's horizontal if the vibration is horizontal. But if it's vertical, gravity will move your equilibrium position down. Okay, so basically the motion of this body is composed by two parts. A static elongation, we call it, delta static, which is the difference between unloaded spring position and equilibrium position. And then the vibration itself. So what do I do when I choose my coordinate systems in vibration? That's important. When I choose my coordinate system in vibration, I put my coordinate system with 0 at the equilibrium position. I don't choose to put y up here. I choose to put it down here. Okay? So that it's 0 when I have the equilibrium position, because I know that then the vibration will be around that point. So it will actually be this formula without a constant here. It will be a sine wave around that equilibrium position. That is 0 if I choose y starting from the equilibrium position. Okay, so I choose y so that the equilibrium position is y equal to 0. Clear? So in this case, if you do FBD, you obtain this free body diagram. Okay? The force now, since this spring is elongated by delta static and shortened by y, the force goes like this, and then it's k delta static minus y. Okay? And mg is going down. So you obtain this equation, my dot dot equal k delta static minus y minus mg. Okay? This force of the spring, which is, this is k delta L, right? Okay, this is k delta L, the force of the spring, is equal k multiplied delta static minus y. Because delta static makes it longer, y makes it shorter. Okay, so in total, the motion is delta L minus y. Clear? So delta L, look at here, is delta static minus y. Clear? So k delta L is k delta static minus y. So that's the equation of motion. Now, this equation of motion, I split it in two. Okay? The first thing I do is that I look at what happens at equilibrium. So at equilibrium, how much is acceleration at equilibrium? If I take this bar and I nicely put it in its equilibrium position and I let it go, how much is the acceleration of this bar? 0 now. It's still. So at equilibrium, acceleration is equal to 0, correct? How much is y at equilibrium? Displacement. Well, if I chose this convention, this coordinate system with y equals 0 at equilibrium, well, I decided that it's equal to 0, so it's going to be equal to 0. Because I put it there, the coordinate system. Okay? So this is also equal to 0. So I'm left with that. That's the equilibrium equation. What does it allow me to find? What can I find out of this equation? What do I know? I know G? Yes, 9.81. Mass and K, usually I know them. It's the mass of my system and the stiffness of my spring. right? So I can find how much it actually moves in equilibrium. I can find this amount, okay? I can find where the equilibrium position is compared to the situation with unloaded spring, okay? That's not part of the vibration, of course, but it tells me where the vibration happens, so around which point the vibration happens, basically, okay? Clear? mg divided k in this case. I changed the convention, I told you, and I missed some force. Okay. Cool. Now, we found this, so we know this variable now. So I go back to the full equation, right? The full equation is this one, Newton's law. Newton's law gave me that. By applying the equilibrium condition, I found delta static. Now, what can I do? I take it and I put it back in the original equation. Why not? I know how much it is, so I can put it back. So I put it back. Here what it comes. K multiplied by mg over k is mg. Minus mg, these two cancel out. And you're left with a very simple equation. Okay? That happens if you choose y 0 at equilibrium position. So if you choose to put y here and not here. Clear? Then your equation is very simple. There is no constant term, and there is no delta static. They cancel out. Is it clear? You only have x, or y in this case, depending terms. No constant term, no other stuff. Once we have this, we know that the solution is the usual, because this is the usual shape of our equation. We found it before. That's the same now. Right? What's the solution of this differential equation? Well, it's y equal, I didn't write it here. Let's write it. Usual solution, y of t equal a sine of that. Was it plus or minus? Sorry, depends on what you choose, sine or cosine and stuff like that. Yeah. There are different conventions in books on how to write this function. Is always the same function. So depending on the book, you might find a cosine here, and then simply the expression of this changes. Or you might find a minus here, and then simply the expression of this variable changes, like how much this variable is. Where is it? Here. This expression will change according to what expression you choose for this. They're all equivalent. I chose one because there are many. Okay? You can stick to this one and it's fine. Okay? So the idea of a vibration problem is this one. Play with the equation. So start Friboli diagram, write Newton's law, then play with the equation to obtain an equation which looks always like this. Once it looks like this, you know the solution is that one. You solve your differential equation without solving it because you know the solution is that one. Okay? Clear? What time is it? Let's take a break and then we do the example. 5 minutes. So, where were we? Example. So, let's see how we solve a vibration exercise or a vibration problem. Okay. So, if I get a pen, I copy this exercise on my sheet. Note that the problem says, okay, the characteristic of the system, and then that the springs are two in this case, but whatever, the springs are pulled to a length of 25 centimeters from the free length position. Okay? Clear? That's where I start. It's not 25 centimeters from the equilibrium position. It's 25 centimeters from the free length position in this case. Okay? Good. Okay. So, first thing we do, free body diagram. Forces. So I assume this as y. I have definitely gravity, mg. Then I have two springs which have two forces, k, delta L, k, delta L, which, how do we draw these forces? The best strategy? Best strategy. There are tons of conventions you can use to do that. To me, the best strategy is assume always delta L positive in traction. Okay, so with the spring which is elongated, and therefore the force going towards the center of the spring. Did you get it? So if I assume that this number is positive, so if I consider this number positive when the spring is actually elongated, then the force will go towards the center of the spring. Do you agree? So if I consider that delta L is positive when elongated, then the forces will go towards the center of the spring. Okay? So this force is going towards the center of the spring because I'm assuming delta L to be, my convention is to write delta L positive in elongation, negative in compression. Good. So now, let's write Newton's law. My dot equal minus mg minus 2k delta L. Agreed? I mean, I could have written minus k delta L minus k delta L, but then they sum up to 2k delta L. How much is delta L? That's my spring, which is not loaded. So it's free length. Then I put my mass on. So this is the free length. I put my mass on. What happens to the spring? It gets compressed, right? So it goes down here. So this I call delta static. Then from here, what happens? That it vibrates. I don't know how much, but it vibrates. So let's say it vibrates by y, and it goes here. That's too big. Let's do a little y. This is y, and it goes here. How much is delta L? How much is delta L? Delta L is from here to here. So this is delta L. This is drawing. I'll do it again. Okay. So it goes down. So this is unloaded. I load it. So I put the mass on. That brings the thing down. Draw it very big so that we have no problem. So this, oops, actually this is delta static. Now this mass moves vibrating by a tiny quantity, y. And it goes here when it vibrates. Yeah, from top to top I'm drawing. Okay. So how much is delta L? Again, I did it. Apologies. This drawing is very annoying. So I have the free length. Then I put my mass on. Okay, that compresses the spring up to here. Okay, so this is delta L. And now it moves by a certain amount, and it goes here. Good, this time I did it right. Okay, so this is delta L. This is y, because I decide to put, this is the equilibrium position. Equilibrium. So I choose y equal to 0 at equilibrium, which means that delta L of the spring, so the elongation or shortening of the spring, is how much? Sorry? It's delta static minus y. Agreed? Are you sure? What did we say before? What's our convention for this drawing? We said that our convention is that delta L is positive when it makes the spring longer, not shorter. Right? Do you agree? So in this case, delta L is obviously making the spring longer, shorter. Right? Do you agree? This delta L is making the spring shorter. In this case, it's shorter than here. So this is a negative delta L, okay? This is minus delta L, so we call it delta L equal minus that thing, okay? That's the most tricky thing of the whole vibration, of all vibration exercises. So you consider delta L positive if it's making the spring longer. Once you see that in your drawing delta L is making the spring shorter, then you just put a minus in front of your expression. Okay? Good. Now that you have this expression, we can substitute it in our equation. Okay, so our equation of motion was this one. So now we can write m y dot dot equal minus mg minus 2k multiplied by minus delta static minus y. A lot of minuses. Let's simplify it a bit. My dot dot equal this minus with this minus becomes a plus, minus mg plus 2k multiply delta static minus y. And I'm assuming, look, delta static in this case, I'm assuming it's this quantity, so it's in compression, right? Delta static is compressing the spring. So I want to know two things out of this exercise. I want to know how much is delta static, how much is the spring compressed when it's in equilibrium position, and I want to know the vibration time. How can I do that? How can I find two quantities out of one equation? Well, there's a particular case, which is equilibrium, which will give me another version of this equation. So at equilibrium, how much is acceleration? It's zero, it's not moving. How much is y at equilibrium? Well, we chose it to be 0 at equilibrium. We put our reference system here so that it's 0 at equilibrium. Therefore, I can rewrite this equation at equilibrium, and it becomes 0 equal minus mg plus 2k delta static, and y is 0. This gives me delta static equal mg over 2k, which is equal to 10 multiplied by 9.81, 98.1, divided 2k is 200, which is equal 0.49 meters. So one thing is found. This guy is found. Agree? Now, if I put this back in this equation, my dot dot equal minus mg plus 2k. Now, delta static, I know it's mg over 2k minus y. I develop this equation, minus mg, 2k multiply mg over 2k is plus mg, 2k multiply y is minus 2ky. Okay? So this equation looks very similar to the one I found before in the slides for the other exercise, right? Still very similar. Now, what do? Everything in front of y dot dot, I call it m star. So this, I call it m star. In general, it could be different from m. And everything in front of y, I call it k star. Is it clear? So m star in this case is equal to m, which is equal to 10 kilograms. K star in this case is equal to 2k, which is equal to 200 Newton over meter. Agreed? So what do I do now? What do I do? Well, I have my equation, and I know the answer, because I know my equation is now m star y dot dot plus k star y dot equals 0, where m star is this number, k star is this number. So I can immediately calculate what? What can I calculate? So I know my solution is going to be yt equal a sine omega n t plus psi. I know because this equation always has this kind of solution. Now, which of these three parameters I can immediately calculate? Omega n, because that is depending only on m star and k star. Okay? So with omega n equals square root of k star over m star, which is square root of 200 over 10, square root of 20, something like 4.47 radians per second. Okay? Now, what about the other three parameters? So I know this number. I want to know these two numbers. What about those parameters? Well, I know the formulas. I know that A is equal square root of x0 square plus v0 square over omega n square, for instance. Now, to find this A, I need x0 and v0. Now, the problem told me that v0 was equal to 0, so I dropped the system from a still position, so it doesn't have an initial velocity, the problem. But how much was x0? Well, we don't know directly, but the problem told us that delta L0 was 25 centimeters. So we know that delta L0 was 0.25 meters. Now let's go back to our drawing here. Like this should work. So delta L0, it means that at the beginning, delta L was 0.25 meters, correct? We have this formula that tells us, we found it at the beginning, that delta L is equal minus delta static minus y, or if you, which is equal to minus delta static plus y. Okay, so delta L0 must be equal to minus delta static plus y0, which means that y0 is equal delta 0 plus delta static. Okay, so in this case, delta static was 0.49, delta 0, 0.25, so 0.25 plus 0.49, which is equal to 0.74 meters. This is a 4. Okay? Good. Once we have y0, what do we do? Well, once we have y0, we can check it in here. This is x0, but in this case it's y0, obviously. Okay? So a is equal square root of y0, which is 0.74, square, plus 0, because v0 is equal to 0. So this is obviously 0.74 meters. Okay? Clear? Psi is equal to tangent, arctangent of y0 omega n divided v0, okay, which is something divided by 0. How much is it? Something divided by 0? No. Infinity. How much is tangent of infinity? Arctangent of infinity? Pi half. 90 degrees. Okay? That's the arctangent of infinity. Okay? Good. So now we can substitute all these numbers back here. We have them all. So y of t is equal a 0.74 sine omega n is 4.47 t plus pi half. What do we know? We know a lot of stuff. Okay, let's see what we know. So we know this, and we know that delta static was, I don't remember, 49 or 25? 49. 0.49 meter downwards, while y is positive upwards. Okay? So we know these two things, and that allows us to draw how this vibration looks in time. So I can draw it in time. This is t, and this is y. Okay? So y is equal to 0 where? What is y equal to 0? The equilibrium position, okay? So this is the equilibrium position. This corresponds, let me find the drawing I attempted 3 times. This corresponds, y equal to 0 corresponds to this position. When the mass is here, it's y is equal to 0. Clear? So I'll draw it here just to remind us that this is the equilibrium position. This has gone down from an initial free spring length position of delta static. You remember that, right? This was like this at the beginning. Forget about this. This is the free length. Delta static brought it down to this equilibrium position, and now we define y equal to 0 here at this position. Cool. So I can actually draw this. This was the free length position, but who cares? Not really important. Okay, and this is actually equal to, how much is that? Delta static is 0.49, 0.49 meters. And now we have a vibration which has an amplitude of 0.74. So the vibration is 0.74. Okay, this is 0.74. And it starts at time equal to 0, so here. How much is it? Y. T equal to 0, sine of pi half is 1. Therefore, 0.75 multiplied by 1 is 0.74. So at the beginning is like this. And then it goes down. And it goes to minus 74. And so on. Okay? That's how it looks. So the distance between 2 peaks, so this distance, which is equal to this distance, is equal to t equal 2 pi over omega n, which is 2 pi over 4.47 about 1.4 seconds. Okay? And the amplitude is here and everything is here. Now we're all done. This drawing is perfectly determined. I know everything of the drawing. Okay? So now you understand why I've said that undamped vibration, undamped system, what does it mean undamped? There is no damper. There's no damper in this system, obviously, right? There's only a spring. Vibrate forever. Why? Well, the vibration is a sine wave. Is A sine omega n t plus psi. If I take t even big, it's going to still vibrate. The sine wave never stops. Right? Agreed? Good. Let's move on. We've seen free undamped vibration with no damper, but we know that if I hit this guy, oh, this is very little damp, but it's damped. So after a while, eventually it will stop. Okay? So everything in reality has at least a tiny bit of damping. So the situation we've seen so far is a very limit situation, is a very interesting situation because it's a theoretical limit, but it's not realistic. Okay? The realistic case has damping. See, that stopped almost. It's going to stop in a while. So what happens in case of a damper? So when I have a damper, I do again the free body diagram. Well, this force doesn't change, same as before. This force doesn't change, same as before. I have an additional force given by the damper, and that is C y dot in the direction towards the center of the damper. I'll put it up there, otherwise I confuse you. Okay, I'll put it where the damper is. Okay. Good. Okay. So it's, if I move by y, the damper is going to resist with cy dot. Is it clear? If you want, I could have done one step more and write delta L here, and it would have been the other way, but it's okay. We'll do it. We'll do it in an exercise. Don't worry about it. Okay? Then I write Newton's law. My dot dot equals sum of all forces. So this one is positive, this one is negative, this one is negative. Okay? What do I do? At equilibrium, what goes to 0 at equilibrium of this equation? Equilibrium means nothing moves. So what goes to 0? Y dot dot for sure. Then y dot, what is it? It's the velocity. Can it be different from 0 if nothing moves? No, it must be 0. So this term goes, this term goes. We also are smart, and we set our coordinate system so that y is equal to 0 at equilibrium. Therefore, also this y goes. So these two go because of equilibrium. This one goes because we are smart in the choice of our coordinate system. And therefore, I'm still left with these three terms, and again, delta static, in this case, is mg over k. Obviously, damper, adding a damper didn't have any effect on static equilibrium, on delta static. No effect. Why is that? Because the force of the damper is c y dot, and at equilibrium, y dot is 0 anyway. So the damper has no effect on this delta static, because this term goes away as soon as I say the word equilibrium. Okay? So in this case, then I substitute this back. This will go away, same as before. I'm left with this equation. So in the case of a damper, very similar to before. Before I had this term and this term. Now I have this additional term. What does it do? Well, you can solve this equation still. Luckily, there is an analytical solution, which is a bit more complicated. Okay. It's a bit more complicated. Actually, this equation can end up in three different solutions depending on the ratio between this term and the other two. So you calculate this ratio, which is called damping ratio. This letter, who knows what it is? What's the name of the letter? Oh, good. This is a particularly good call. Nobody knows what symbol it is before, usually. Very good. Okay, it's zeta, okay? For those of you that don't know the difference between, it's very common. I always fight with my desk mate, which is control lecturer, because he cannot draw them differently. I always mock him. So this is zeta. This is xi. Okay? Zeta xi. Okay? Now, the question is, do I get picky if you draw zeta and xi? No. Actually, if you look at many books, they use them interchangeably for this term because a lot of people cannot write them differently. Okay? Since a lot of people cannot write them differently, they said, okay, let's do a nice free-for-all. And basically, if you call this xi, it's still okay. So you can draw it either as a xi or as a zeta, and it's fine as long as you know it's a damping ratio. Okay? Luckily, at least in vibration and in dynamics, they are not usually used for any other thing. Both of them. Okay, that said, you have to calculate that damping ratio, which is this number, so the number in front of the y dot, divided to this number, omega n. How much is omega n? How much is omega n? Same as before, with omega n equal square root of k star over m star. No, 8. I didn't want to write 8. I'll write star. Okay? So what you do, when you obtain this equation, you have the numbers for this, and for this. You can calculate omega n immediately by the square root of the ratio of this, and then you can calculate zeta with the ratio between this, and 2. Okay? So you can calculate these two numbers. Very philosophical question now for you. Coming. This zeta parameter, is it more similar in nature to omega n or to the amplitude thing we saw before, this A and this psi? So is it similar to those two or this omega n in nature? Conceptually, what would you answer? Similar to omega n or similar? I know it's a very, very weird question, I admit, and I will give you the answer anyway. But what's the most is more similar to an amplitude or is more similar to an omega n? Omega n, why? Exactly. It only depends on the parameters of the system, not on what I do to the system. You see, there is no x0, velocity 0. Doesn't depend on the initial condition. It doesn't depend on where do I put this bar. It only depends on how much is the stiffness of this guy, the damping of the damper, and the mass of the system. Clear? So it's a property of the system as omega n. It's independent to what I do to the system. It's like the mass of the system. It's a property of the system. Once the system is done, that's it. It's zeta. You cannot change it by moving the system. Okay? Clear? This parameter is massively important. Massively. Because it affects not only the numbers in the solution, but the actual function. Is it a sign or not a sign anymore? Okay? This kind of thing. And we see the 3 cases. 4. Yeah, there are basically 3 because one is very similar to the others. Zeta equal to 0. We already saw it. When is zeta equal to 0? Look at 0. Zeta is c divided m omega n. Only if c is equal to 0, then zeta is equal to 0. But if c is equal to 0, this is not there, and we are in the previous case we've seen before. So it's undamped. Okay? So if zeta is equal to 0, we have already seen the solution. Basically, there is no damper because there's no c. So this guy is not there when zeta is equal to 0. So zeta is equal to 0 is undamped solution. How does my function look like if I have undamped vibrations? How does my vibration look like in time? What's this function? It's a sine wave. So if zeta is equal to 0, my system is going to vibrate forever because it means that c is equal to 0, which means there is no damper. Clear? Good. If zeta is between 0 and 1, we called those underdamped vibration, not undamped, underdamped, which means damped but not much. In this case, we have oscillations, but decreasing in time is the typical case. If I hit this bar, I have oscillation. This bar vibrates, but less and less in time. Its amplitude goes down in time. If I have zeta, and I'm going to chuck together these two cases, equal to 1 or greater than 1, I have no oscillation. My system doesn't even oscillate. I'll give you an example. If I drop a mass on a pillow, right? A very nice and soft pillow. Will it vibrate? No, it will do and sit there. Okay? This is no vibration. If I jump on one of those nice old beds with springs, that will vibrate. So this is the difference. The pillow system will be one of those. The bed with the springs will be one of those. Clear? Mathematically, this, which is the most interesting, obviously, what is the most interesting case? This one. And this is the most common, in mechanical systems at least. Okay? Mechanical systems very often always have damping, a little bit, but they have it. And that damping is usually tiny. What tiny means? Less than actually 0.1, so it's even closer to 0 than to 1, okay? Usually damping is very low, at least for a range of frequency which is below 100 hertz, okay? So normal machines, if you hit them and you see how they vibrate, they'll vibrate like this. So vibrate and then slowly damped out of their vibration, okay? Like this system here. That's common in mechanical engineering. These cases happen, but less often. Okay. So in case of this, if I have zeta between 0 and 1, when I have underdamped vibration, so vibrations decreasing in time, this is the equation. It's a bit more complicated than before. You remember before we had A and a sine wave. That means the sine wave will live forever. That's the case of without damper. With the damper now, I have this additional term, which is a function that looks like this, the dashed line here. You see, that's this function. Now, if I multiply this function by the sine wave, I obtain a sine wave which decreases in time. Clear? So that's how the vibration looks like, the blue one. It's still a sine wave, kind of. It's not a sine wave, but it looks like a sine wave, but it's decreasing in time, in amplitude. Okay? Clear? Good. What about the frequency? What about omega d? Why is that omega d and not omega n? Omega d is slightly affected by the damping, so it's not omega n anymore here. The frequency is not omega n anymore. It's called omega d, or damped natural frequency. And it's omega n square root of 1 minus zeta squared. So since zeta is a positive number, square, it's positive anyway, but it's positive, square is positive. 1 minus a positive number is always smaller than 1, and its square root is smaller than 1. So omega d is always a little bit less than omega n. So what are the two main effects of damping, of adding a little bit of damping to your system? Two main effects. One is major, one is secondary. Major effect is that your vibration will not live forever. They will slowly go down. Second effect is that your frequency of vibration is slightly diminished by the damping. Why do I say slightly? How much did I say is the common zeta for mechanical system? Less than 0.1. So let's take 0.1. 0.1 squared, how much is it? 0.01. So 1 minus 0.01 is not much of a number. It's still very close to 1. So these two, in practice, for common zetas, they usually look very similar, omega n and omega d. With omega d slightly less than omega n. That's the common case. Okay, clear? Any question here? What is A here? Well, A tells me the amplitude at the beginning, not even the actual amplitude of this function which multiplies the sine wave, but it's more or less the amplitude at the beginning. A, okay? So this kind of amplitude. Is it clear? That's the actual value of A. Explaining it is more difficult than everything, okay? But basically it tells me more or less how much is the amplitude at the beginning. Clear? Here, an example of the effect of omega d. So omega d is equal to omega n of that. So what happens if I increase zeta, keeping omega n constant? How do I do that? How do I increase zeta, keeping omega n constant in a system? What do I do? So I have this system. I want to keep omega n, undamped natural frequency constant, and increase zeta of this system. What do I touch? C. I increase C. Because if I increase C, omega n won't change. Omega n is this value. K and m affect omega n only. And C will increase zeta. Bigger C, bigger zeta. Okay? Omega d then will follow, but who cares? We said if I want to keep omega n constant and increase zeta, then I increase C. Okay, so I increase C, and I get these values of zeta with the same omega n. Now, with zeta equal to 0, what do I have? I have undamped vibration. The black one lives forever. It's a sine wave. With a tiny zeta of 0.1, actually it's not so tiny. Blue one is already quite decaying quite fast, actually. Okay? But it's still vibrating, obviously, because zeta is less than 1. As I go up with the damping, the vibration dies quicker and quicker and quicker, until for a level of zeta equal to 1, it doesn't vibrate at all. Already 0.7, you see. It does one cycle and it's done, basically. Okay? Clear? The frequency, omega d, is affected by it because you see that, look at how this is one period, and then when I increase the number, this moves a bit further on, making the period a bit bigger, which means the frequency is a bit lower, but not much. As I said, the effect on the frequency is very tiny. Okay? So omega d changes, but not so much. This is a much more interesting example. 0.5 underdamped, blue one. Zeta is less than 1. So it's vibrating, and the vibration is dying out. Zeta equal to 1 or bigger, it simply doesn't vibrate, you see? It doesn't oscillate around the 0. It's going down to 0 without any vibration. Is it clear? Is the pillow situation. Too late. For that, this one has solutions online. I'll upload them as soon as I get back to my office. Okay? Next time we'll do vibration again, so don't worry about it. Oh, so I haven't had time to speak about the exercise. Okay? Only a couple of things I want to say. I was asked if in the PST you can neglect air resistance. Obviously. Okay? There is no coefficient I give you, so obviously you cannot neglect. You have to neglect air resistance. And if you had no other question was particularly general, like there were questions, personal like questions, but not general. So if you have any other question, send me an email or contact me. If you have something very quick, you can send me an email. I can answer by email. That's the fastest. If you have something more like that you want to discuss with me, just send me an email. We fix an appointment. But do it quick because the deadline is now approaching. So don't do it in the last 2 or 3 days. Okay? Thank you.